Thank you very much. It always cracks me up. Here you have a technology-based conference, and you struggle with the projector. It happens every time. It never fails. I am really honored to be here today as an alumni. I have to say, when Rod and Dr. Shoup from the Biomedical Engineering Department called me up and asked me to give a talk and get involved, I'm like, are you really sure you got the right guy? I was definitely not one of your better students. It took me 6 years to graduated with 2.934. I barely squeaked into grad school, and it's like, are you sure? You want me to be the one trying to motivate your students? And Dr. Shoup said, well, what's important isn't necessarily the grades you get, but how you apply the technology afterwards. And the way you've applied what you've learned, you're now one of our best students. So remember that if you're struggling a little bit with your grades from time to time. So first, just to tell you a little bit about myself and Mimic Technologies. We are a company that spun out of Seattle. I did do my undergrad here, graduated in '93 with a degree in biomedical engineering. Went on to Northwestern, Chicago area, did 3 years of a master there. So as you see, there's a theme here. I spent a lot of time in school. And then finally went to University of Washington, which is where I did my PhD work. That's about the only degree I think I finished on time at about five years. So I guess I just really liked school, and it took a long time to get out and do something with what I had learned. But I did meet a lot of folks at the University of Washington, worked at the Human Interface Technology Lab. Matter of fact, I started the company with a lot of people from the University of Washington, and as the company grew, tended to hire a lot of people from the University of Washington. But now we're expanding and kind of recruiting all over the world. I guess the University of Washington element of our company is starting to diminish. We are a company focused on robotic simulation and force feedback technology, and I'm going to talk about these technologies today. And when I started the company, tried to start it in a relatively traditional sense. Back in 2001, started talking with some friends of mine, two individuals who had both business degrees and law degrees, so I guess they're the ultimate evil, right? So, but no, they were very good guys, and I can't say enough about Mark's presentation because all that stuff is so important. Back then, all I wanted to do was be the CTO. All I wanted to do was just deal with technology and build technology. And you can't just have technology without a plan in place. How are you going to get it to the market, or even understand whether a market exists? So this is where these business people are crucial. Hopefully you can get Mark to share his presentation, because that is a blueprint right there for what you should do when you build a company. I wish I had done more of that, frankly. Now here's the problem with when I started the company. It was back in 2001, which was about the time that the internet bubble. So here we are. We've got this business plan together. We're about ready to go out, start getting investors, and that's about the time that all the money went away. And from that point on, I think it was over 2 years before a brand new company in the Seattle area got funded. So I actually had to do it the old-fashioned way, and that's go out and get contracts and make money. I used to joke at the time when I started the company, I think I was the only PhD on food stamps. But I believed in what we were doing, and I figured all I had to do was just kind of wait out long enough, and then eventually the money would come. And it did end up coming in the form of Department of Defense grants, which I'll tell you a bit more about it. So we ended up being a completely self-funded company, and most of our R&D was done with grants. This has its advantages and disadvantages. One, I had to live poor for very, very, very long. And two, it probably took us a lot longer to get to market than would have been necessary with proper venture funding or angel funding. On the flip side, I don't think we necessarily knew what we were doing or had a good path forward. And if we had taken a lot of money in the beginning, I personally believe we'd be out of business. So I guess I'm sort of showing you two sides of the coin here. Everybody's different, but hopefully I'll share with you my experience, and maybe hopefully at least be entertaining. And our flagship product is a simulator that we built to support the DaVinci surgical robot. The DaVinci surgical robot is what you see off to the right-hand side there. The middle video is actually a competition that's going on from two simulator users. So believe it or not, surgeons are very competitive. Turns out they really love competing. So what you do is you actually sit down at a surgeon's console that looks a lot more like the one on the left here. So I guess I should have a pointer. And that controls the robot. So you've got your master on the left that's controlling the slave in the center there. Oh, perfect. There we go. So master, slave. And this is a company that it pretty much has a monopoly right now. What you have over here is what we built, and this is what you have here today, and this is a low-cost emulator of the surgeon's console that allows people to train and prepare to use the robot instead of learning on people. And I'll get quite into a whole bunch of that as we continue. So first of all, what are our core technologies? As I mentioned, we're a haptic device company, a robotic company. So you need your hardware, and that's what this is. This is a two-handed haptic device. By haptics, I mean it delivers the sense of touch in a virtual reality environment. And if you're going to do the sense of touch in virtual reality, you have to have two things. You have to have good hardware, and you have to have good software. So my PhD focus was finite element modeling, in particular, how to take an engineering method and make it real time so that you can use it in surgery simulation context. It's typically very computationally intensive, something I'll talk about at least a little bit. And you have to have something to work with, so you have to be able to generate the models of your anatomy if you're going to do a procedure specific or surgery simulation in general. So first of all, what is haptics? Haptics is the science concerned with the sense of touch. This is a quote I really, really like. Touch is a symphony of sensations, a multitude of instruments contributing their voices each in their own fashion. So what do I mean by this? What it means is touch is not a single sense. You're just receiving input when you're hearing or seeing or tasting, although tasting does have some force feedback, I suppose. But with touch, you're exchanging energy with your environment, and you react based on what the environment gives you. So this is very, very difficult to model. You have to do it at very, very high rates, unlike vision, where you can take 30 still frames and put them together in a second, and you perceive animation. If you want to perceive touch or force feedback in an environment, you have to do this at a much, much higher rate. If it's a soft object, about 300 times a second. If it's a solid or rigid object, 2,000 to 10,000. It could be much higher. And then if you really, really want to do good force feedback, you have to take into account vibration. Whether this feels like wood or plastic or metal, that has to do with the vibrational response. And that gets into tens of thousands of changes. So it's a very difficult sense to work with. Now, just a little bit of lingo here. A lot of times haptic feedback is used interchangeably with tactile feedback and force feedback, but really this isn't the case. Haptic feedback sort of encompasses both tactile feedback and force feedback. And tactile feedback refers to sensations. So is it going to be texture? Maybe it's temperature, pressure, vibration. Force feedback is directional, where you have a vector of force. So when I push against this wall, I have an equal opposite force pushing back so that all your forces balance out. If they don't sum up to zero, you have motion, right? So this is something, so that's the difference between tactile and force feedback. So how is the sense of touch delivered typically in a virtual reality environment? The most common is really using what's called a linkage-based haptic device. So somehow you're putting torque at the joints of your robot, and the motors don't necessarily have to be located at the joint. They can be run through cables, but that's the general concept. And then the user sort of holds the end of this linkage chain, and by combining the torques at the joints, you end up with the resultant force at the end, the grip, if you will. So it's not a bad system. However, what happens when you want to change the workspace size? Well, let's say we want to keep that same applied force that that smaller configuration allowed for. Well, you can see two things that have happened here. One, this link has grown much larger or longer, and we've had to, as a result, make our motor force much bigger. This is because you now have more of a lever to push on these joints. So as you see, as you try to represent bigger environments with haptics, so this is going to be your cave type environment, or a holodeck, let's say. You know, everybody wants to have force feedback in a holodeck. You know, this is a hell of a challenge. So there's certainly limitations to this design, and the other big problem when these things get bigger is they become more heavy and you have more mass and momentum to deal with. So one of the things I believed from the very get-go is this just wasn't a very flexible solution. So we wanted to see, and even probably more important is there's tons of patents out on this kind of stuff, so it's very, very difficult to own your own technology if you want to create a linkage-based haptic device. So we took a different approach. We took an approach based on, well, first of all, here are some examples of various devices. This is actually pretty intriguing. This actually came out of, well, at least Tom Anderson from the Human Interface Technology Lab up in Washington, he decided to try to take haptics to consumers. So this is actually only about $300-400, when typically a haptic device such as this one is going to be above $10,000. This one I believe is in the $50,000 range. So they're expensive. And if you want to be a software company, that's a huge cost of your product eaten up on hardware. So we wanted to take a different approach, which is relatively simple, and this is called a tension-based haptic device. What you have is you have either a grip, or in this case your finger, where you have 4 cables attached. And the way you get a single vector of force is you apply tension to each of these cables, and by varying the tension in those cables, you end up with 1 vector of force. So it's a very simple concept, but it's very applicable, and there's a heck of a lot of advantages. One, you can see right through to the screen behind you. The reason this is blurry is because this is actually a 3D image that's being projected out to the user's hands. If you had a linkage-based device in front of you, your eyes might focus on that linkage-based device rather than the screen. You wouldn't be able to see 3D. But it's very flexible also in size. You can see because we are now dealing with vector forces. You don't have this lever effect you have to contend with. You can also adjust your degrees of force feedback. So in this case, in this video right here and the one that follows, this is just 3 degrees of force feedback. And the way you decide how many cables you need is you take the degrees of force feedback you want, you add 1, and that's how many cables you need. So in this case, 3 degrees force feedback is 4 cables. This one right here is a 6 degree of force feedback device. So not only do you have translation force feedback, you also have rotations. Add 1 more in, make it a nice even 8. You can have grip force feedback. This is, as you can see right here, this is a great example of having that transparency of your cables and to be able to interact with media behind your force feedback device. And then, of course, the scalability. So here we have a room-size haptic device. So this is, and remember, you can use the same controller board, the same motors. You have a little bit of mass building up because of the cables, but in general, you can take a very modular type of design, place your motors where you need it, and that defines your workspace. So how did we apply this technology? And remember, this is sort of a medical device talk, so hopefully you're not squeamish. But this is one of our very first efforts. So when I graduated, I was partnered with some folks at the University of Washington, and we built a haptic device that could fit right within this little model right here. And this is called transurethral resection of the prostate. As a male, your prostate is a ticking time bomb. Eventually it is going to grow, and urine flow becomes more difficult. So TURP is used to sort of clear out that pathway. It's pretty brutal. But you can see the general idea here. So this is what's called a Receptive Scope, and at the end here you have 4 cables that are attached to the end of your Receptive Scope, giving it force feedback. And then when you put the skin back on it, you have a simulator. So we started this. We began the work. We worked with a company called ACMI for about 2 years, mostly doing work for free, just trying to get to the point where they would adopt this technology. Our thinking being that if you train with the vendor's scope, and when you finally go out to become a practicing surgeon, you're going to use the tools that you trained with. This worked very well for the first CEO that we worked with. Problem is, the last year there was about 3 CEOs that kept changing control. And I think when we got to the 3rd CEO in our 2nd year, he decided that he did not want to do simulation technology anymore. I don't think I ever received a call back from that company, not even telling me we weren't working together anymore. So that was a fun first experience. But you move on and you adapt. So the next company we worked with was a company called Symbiotics, and they wanted a laparoscopic force feedback device. Everyone was very worried about laparoscopic force feedback, at least companies that were very focused on simulation. The reason being is one of the companies we work with now called Surgical Science, they had licensed this, or at least purchased haptic devices for laparoscopic surgery. By the way, what laparoscopic surgery is you put some holes in the abdomen, you work through these very long tools, and as a result, it's a minimally invasive procedure. This became popular in the 80s, 90s. It's one of the reasons simulation really got started, because very similar to robotics in effect, when people started using it in the early days, there wasn't much in the way of a training modality. So there were deaths, and as a result, the government started investing in laparoscopic simulation. Pardon me. So this company Immersion was making it was a decent laparoscopic force feedback device, and Surgical Science decided to build a whole product line around this hardware. So guess what happened? The company that made the laparoscopic hardware decided to duplicate the software that this company Surgical Science was making, and then would no longer sell it to Surgical Science. So they almost went under as a result. I really took this lesson to heart when building a company, and this is really one of the reasons I thought we just had to have our own haptic device technology. But this was a prototype that we built up, but unfortunately while we were building the prototype, Symbiotics became very concerned with time to market, a concept that we discussed in the last talk, and as a result decided to take another company's very, very, very expensive haptic device and decided to go to market with it. So next thing you know, that's the second project we're out on. And that was so now we're about 2.5, almost 3 years in, and we still haven't got a product that we've had any kind of traction with. So we had started building some examples of haptic devices. So this is a one-handed haptic device that we call a Mantis Workstation. This was a prototype for a company called Accuray and a product called a surgical robot called the CyberKnife, where the surgeon actually digitizes, and you basically you're reduced as a surgeon to tracing organs on a slice by slice basis. So what we wanted to do is make it more of a 3D experience. Surgeons don't sit by a mouse all day. They don't move a mouse on a pixel by pixel level. It's very, very difficult. So we wanted to bring haptics into the component, give a 3D viewing. And this is really where we really started making our mark, and this is with a two-handed haptic device. Again, you can see we have this sort of passive display. You're actually seeing some early work we did with DaVinci tools, and one of the very first applications we tried to do, which was prostatectomy. We're suturing the urethra to the bladder neck after the prostate's been removed. So this is where we finally started to get some traction. But here we are, a company without a real application. So before I get to the applications, I'm going to tell you a little bit about some other technology. And as I mentioned, you have to have hardware, but you also have to have software. And everyone loves to make the analogy that, well, it's just like flight simulation. You know, no one ever trains on that really, really expensive plane. And it's also dangerous, right? You're going to take this multi-million-dollar jet fighter up into the air. That's not typically how you should be trained, or at least it makes sense, right? Although this is how a lot of surgery is done. People learn on people. And in the case of the DaVinci, that's a very expensive piece of equipment, but there wasn't an alternative, so that's how it was done. The problem with this analogy is that the modeling is much, much more difficult for the human body. Just to throw a bunch of engineering terms at you, biological tissues are considered highly nonlinear, inhomogeneous, anisotropic, viscoelastic, often pre-conditioning, stress relaxation, pre-hysteresis, blah, 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 blah. So anyways, it goes on and on and on. It's very, very difficult, even offline, let alone real time, to model tissue realistically. And the general perception out there is that, look at these video games, they're so realistic. Well, you'll notice there's not much definition in video games. And second, they don't really have to be realistic because it's a video game. Third, they've got about $100 million budgets, more than movies these days, so there's a heck of a lot of resources making those as realistic as they are. So considering that surgery simulation is still very, very new, I would say that there's no surgery simulation company that's making money anywhere close to any kind of gaming company. So it is a challenge. So this was my PhD work, which is to try to bring some realism back to simulation. This idea of using material properties, and this is like one of the real-time finite model that I did as part of my PhD work. And the way this concept works is if we have a cube or a tetrahedron and we know what that material is, we can fix, say, one face of that, and we can push anywhere on that cube or tetrahedron, and we know how it's going to deform. Now, you can build more complex objects, just kind of like Legos. You take these objects, they don't have to be perfect cubes, you can tweak them a little bit, but the more you tweak them, the less accurate they get. But what you end up with is something that's representative of a more complex object. And the more elements you have, the more accurate you're going to be representing this system. Now, this is very typical in engineering. You probably don't have to tell a lot of you guys this. If you're going to build a car frame, rather than trying to figure out if this car frame is going to crush appropriately without crushing your driver, you don't build a bunch of car frames and test them, but you do a little bit, but you model it first, right? So you model it as best you can because it's a lot cheaper to do this modeling in the virtual space than it is to do it in real life. So my PhD work was finding a way there's some information that falls out of finite element modeling that maybe the user doesn't care about. Most important, they care about that haptic interaction right there. The stress strain that you see right there, it's nice to get a color plot. But the way finite element modeling typically works is you apply, say, a load path, you go to lunch, you come back, and you see your results. But remember, haptics is a bilateral exchange of energy. When you push on this object, you might have a goal in mind. You're going to react based on the force coming back. So that's what kind of my work made a little bit different, and has kind of brought this engineering technique to surgery simulation. And to be honest, we're still in the process of working it into our product line, because which I'll get into. We started with some more basic concepts before going to anything too advanced. After making the mistake of starting with too advanced of an application. So how do you bring this to medicine? It's really simply a matter of putting a texture map on these models. So in one case here, we have an example of suturing using FBM. Here is just kind of playing around with a urethra, prostate, and bladder model using the DaVinci. But that's really the idea is once you decorate these 3D models, they can interact, and if you get the proper lighting, you can make it look pretty realistic. Now, most of the modeling I'm doing at the moment is typically non-linear, or is linear, I'm sorry, which is not the way tissue is. But most people are essentially trying to use video game types of technology to create simulation. That's why when you try a lot of simulators out there, every organ deforms the same. Most of the organs don't deform anything like what you've seen in real life. So it's a step up, but it's far from being where it needs to be. But of course, the goal here in surgery simulation isn't necessarily to perfectly predict what happens. It's to get people up the learning curve. So if you have a product that can get somebody up the learning curve without them having to practice on a patient, then you've really got something. That's just some publication information. And you do have to generate your models. For the engineers in the room, you might find some of this interesting. We talked about earlier about this idea of surgeons having to sit down and contour organs. This is how you start by building a 3D model. Well, what we wanted was a representation of this model that we could create this finite element mesh with. So we start by creating our console, creating what's called an implicit model, An implicit model is simply an equation. You plug in your coordinates. If you have a negative number, you're inside the object. If you have a positive number, you're outside. If you're 0, you're right on the surface. Well, you can blend these slices, these implicit slices together to build a 3D representation. And what we do is we just inject a bunch of particles. They repel each other. They spread out. Then you mesh it, create that finite element mesh. You decorate it with texture maps, and voila, you have content for surgery simulation. So one of the things that Mark talked about was this idea of not getting too attached to your technology without knowing you had an application. Our problem was more that we had too many applications. We had, some people say, oh, we got to go into gaming. No, let's go to computer-aided design. Yeah, we can use computer-aided design and make this a 3D haptic experience. And what about surgery simulation? So it was really hard in the beginning to focus. And then the projects that we did focus on failed. So I was very fortunate to work with somebody named Dr. Rick Satava at the University of Washington. I mentioned the funding of surgery simulation in the late 80s and the 90s for laparoscopic surgery. A lot of this funding came out of DARPA. And Rick Satava was actually the one in charge of distributing a lot of this money. So I worked with him on a couple grant projects. So after, I think about early 2003, I went to Rick and said, here we have this technology, we haven't really succeeded yet, what do you think we need to focus on? And immediately he was surgical robotics. We have a situation where we have a very complex tool that people are just starting to use, and we have no way to train with it. You know, if your robot's weight, it's like the jet fighter. Not everybody can get into that jet to train all the time. You need something that's an alternative to get access to training, because hopefully if you're using your robot well, it's being used in surgery all the time. So Rick came to said that if you can create a robust platform that will model a variety of robots, I'll get you some DARPA funding. So this was the start of funding for the company. And this is a concept right here known as the trauma pod. The idea being that soldiers often bleed to death as they're being evacuated. So if you can get them attention remotely before right when they leave the field, the thinking is that you could control bleeding and save more lives. It's a concept that assumed there was a defined battle line. So talk about a changing landscape in business, right? There's also changing landscapes in war. We used to have defined battle lines. Now we don't really. You never know when a Humvee is going to be hit in Iraq or Afghanistan. And considering these are multi-million, if not billion-dollar pods, not every Humvee can have one. So as a result, the project actually has stagnated and not really gone to completion. But the good thing is Rick, when I was talking to him, told me, hey, well, we don't have this robot ready yet, but as long as you make a platform, you know, you can use a commercial product as your model, and then when we have our trauma pod ready, we can apply that technology. So we started with a company called Computer Motion. I think by the time we had submitted in between the time we had submitted our proposal to work with Computer Motion and got the funding, Intuitive Surgical had purchased Computer Motion, and I was very fortunate enough that Rick Satava was able to talk Intuitive Surgical into tolerating me essentially for the first years. Basically his line was, well, I'm funding them, you guys just have to give him just a little bit of support and just see what he can do. And it only took me from 2003 to 2008 to convince Intuitive Surgical that we actually had something here that they should really get behind. So yeah, very, very short product development cycle. So back to this product, and that's really what we have here. This is the DV trainer. So this is an emulator of the surgeon's console. Let's tell you a little bit about some of the advantages of the system. Well, first of all, we did get our very, very first prototype out in 2007. And we beta tested it and had certainly a lot of problems along the way. We had reliability issues with some of our hardware. So we did not get to release what you see here today until the very end of 2010. So here start the company in 2001. Do not have a released product until the end of 2010. That's a long time to survive without funding. And as I said, you got to be willing to live poor for quite a long time. It's as you would expect, to use virtual reality to teach people to use the DaVinci surgical robot. We're focused mainly on basic surgical skills. You can see here we're dealing with needle driving. You saw a movie a little earlier, which was, or at least some images related to prostatectomy. The problem we had is, this is back in 2004 or so, we would get this very complex procedure that's very difficult to do and sit people down, and people were like, well, what do these pedals do? And whoa, I don't get it. What's the wrist motion? It's not a reversal of your motion like you have in laparoscopic. It was kind of when the lights went on and said, geez, we really got to teach people the basics. And back in the day, the dirty secret was that even though it's intuitive technology, the robot was relatively difficult to use for a lot of people. And a lot of people will argue this. However, the fact is, only 1 out of every 10 people being trained to use the DaVinci actually went on to be a DaVinci surgeon. So talk about defining a need, right? There's a need for you right there. Finding a way to get surgeons who are willing to train to go on to become regular surgeons. And the reason is because it might be 30 days to 60 days until you get your first case. Well, your skills degrade really quick, and considering you may have only had a 2-day class in preparation, and then the next thing you know, you're doing surgery on a person, a lot of surgeons just wouldn't do it. Others would try their very first case, it would go horribly, and they would never ever use the robot again. So what we wanted to do is give these surgeons who had done less than 10 DaVinci cases, we wanted to give them access to this training so that they know how to use the robot when they get on their first patient. So that way they can focus on the surgery. It's kind of like, do you really want to learn to drive a stick shift in San Francisco while you're also learning to navigate a map around? It's like, this is just too difficult. You just can't handle the middle load. So that was our focus, but we did find out that there were other applications, in particular refreshing skills. Some surgeons, and it was a big Wall Street Journal article actually, that talked about smaller hospitals that didn't have a very big caseload. People were going so long in between DaVinci cases that they were making errors, and as a result some people died. Became a really big deal in the news. So certainly if somebody had access to training in between their surgeries, maybe these errors wouldn't have happened. There's also warming up before surgery. In sports we warm up, right? Baseball, you go to the batting cages, driving range for golf, but surgeons do not typically warm up. So this idea that you can wait around while the simulator's being set, or while the robot's being set up, in practice, and warm yourself up both with cognitively and with hand-eye motor skills, studies have proven that you will perform tremendously better. Well, kind of depends on the individual. For example, if you're a resident that's been up all night and you're completely sleepless, your performance usually starts really bad if you jump right into a surgery, but if you warm up, you can bring them back to baseline so that it's as if they had a full night of sleep on it. That's just one of the groups where surgical warm-up applies. So the benefits, obviously, you don't have to have the actual robot. So this way, if a robot's in surgery or in the OR, you're going to even have access to it. So typically people will come in on nights and weekends to train, or this is the way it used to be. So that means you got to convince your proctor and your setup team to come in. And then what are you going to train on? If you cannot use a clinical robot with animals. So your content is relatively limited to Drylabs, and we'll see some examples of Drylabs in a little bit. But the content is limited. Your feedback on your performance is based on your proctor, and some proctors are going to look at things differently. So it's really not a very effective way to train. Now we do model. There's 3 different robot models currently for intuitive. The standard is the first they came out with. There's the S, that's representative actually what you see here, that's what these pedals are. We just started shipping our systems with SI foot pedals, so we are representing all 3 robot models with one single system, which is kind of nice if you're a university or a hospital that has more legacy robots and then some new robots. You can use one simulator to train with both. And remember, these robots are about $1.8 million. So it's very, most hospitals cannot afford a training robot. I believe they can here, which is kind of nice. That's very fortunate. But the smaller hospitals, smaller universities typically can't afford a robot that's going to be dedicated just for training. Now this is really where surgery simulation provides value. And this is objective assessment of your performance. And I'm going to talk about the types of metrics that you would look at when I talk about validation and how you decide whether a simulator is worth a damn. But this is something that you do not get with standard medicine. See one, do one, teach one. It's usually the surgeons giving feedback. Now there'll be some metrics that they may use, blood loss, the time of a case. But you can really, because you know everything that's happening in a virtual environment, every collision, every contact force, everything, every foot pedal they step on, there's a heck of a lot more information you can bring through surgery simulation to assess whether somebody is getting better or not. And you can guide somebody through training, well, hopefully very much more efficiently than if you do not have structured feedback on performance. But no matter how much we talk about wanting better patient outcomes, you know what it really comes down to? Training costs. Right now, a hospital likes to have a proctor with a student in the OR to train them on humans. Why? Because they're billing out for that proctor's time. If that proctor's tied up training somebody, let's say in a Drylab, they're not making any money. And some of these surgeons are extremely expensive. If you're a robotic surgeon, you have a very, very valuable skill. And surgeons, or hospitals pay top dollar to bring you in to hopefully educate your team. So the idea that you can use a simulator instead of this $1.8 million robot, and by the way, every time you turn this robot on, there is a cost. On average, if you're in surgery, it's about $2,000 for all your disposable instruments. If you're using training tools, it is less, but there's still a cost associated. And then you still have OR time, Drylab, the Drylab of whatever the content is you're working on. So certainly you can start seeing here, there is a cost-benefit analysis to surgery simulation, finally. The problem with laparoscopic surgery simulation is that you can have this expensive $80,000, $100,000 laparoscopic simulator, and then you say, okay, well, what are my alternatives for training? Well, you can get a shoebox, some tools, a webcam, a ham hock, and you're suturing. Well, that's pretty cheap. And if even though it may not be giving you the performance feedback you might want, it's cheaper. And I tend to believe that people are going to take the cheapest route to training. So while we'd like to say that we really want to look out for the patients, and we want the best trained surgeons to deliver the best standard of care, cost is always an important element. So this is why laparoscopic simulation did not necessarily take off and become a real big moneymaker. Don't get me wrong, it does well, but robotics was one of the first applications of surgery simulation where there was a very, very serious cost-benefit analysis, and as a result, we only released our product in 2010, another product, oh wait, let's see, I think I have that next. We also ended up taking our product and embedding it into the surgeon console itself. I remember when I said in 2008 Intuitive finally got behind us. Well, the reason is they were coming out with a new robot. I remember getting the call and them saying, hey, can you come down to talk about surgery simulation? And it was kind of like one of those eye rolls on the cheese. I've been down there, every other month trying to pitch this idea. No, we're serious this time. So go down and they say, well, we've got this new robot coming out. The foot pedals are different. There's more icons. And I remember, talking to their VP of engineering, and you can see the stress in his face. He's like, we don't know how we're going to teach people. We teach people by applying what they call a clinical sales rep. And adoption is going up so quick, we can't just keep hiring people. We can't train them fast enough to provide proper training. We need something else. So we work to take our software and embed it so that it will run on the surgeon console itself. The other biggie here is that when the S and the standard were the main robots being utilized, if you disconnected the robot, then the surgeon console would shut down. When they made this, they made it so that it would not shut down, and they thought ahead and said, well, we're going to be able to unplug it and attach a simulator in place of the robot. And they sell this directly and started in January of this year. As a result, we have, by the end of this year, we're going to have well over 400 simulators out there in the field. And now this is unprecedented adoption. No surgery simulator has ever been adopted so fast, ever, not even close. Give us another year or so, it'll probably be the most widely distributed simulator that exists. And I'm talking a combination between skills simulators and DV trainers. just so you kind of get an idea of the kind of ratio. Intuitive's a $1.67 billion company, I believe now, 700 some sales force. For the longest time, you're looking at the sales force for Mimic. So we've got about 100 and some simulators in the field. They've now sold about 200, almost 300 now. So they've got a little bit of a more ability to market and get the product out. But there's different places for these two products, and they do complement each other. If you're going to do surgical warm-up, heck, why not have this right in your lab, or right in the OR? You can actually use the robot to warm up while the setup team is attaching the robot to the patient, if you will. If you're a institution that has dual consoles to operate one robot, this is sort of the driver's ed mode of surgical robotics. Well, that extra console is typically not used on every surgery, so that can be kind of taken out of the OR, and you can attach one of these backpacks to it, and you can use it as a simulator. Great applications of the skill simulator. But what about a sim lab? A sim lab is typically a lab where you've got tons of people that have access, med students. Are you really going to let them work with a $500,000 console? That's the cost of the surgeon console. I know very few people that have one in their lab. It's mainly because of a cost. Some people do. Some people have the money to do so. But your smaller institution that can only afford one robot, again, it's access. What good does this do you if your robot's always in surgery? So this idea of access and cost is important. And since our simulator's less than $100,000 compared to this $500 console plus about $85,000 for the simulator on top, there's definitely a cost. But hey, you can see right here, we have these cables. You're going to have some limited range of motion that you're not going to find on the actual console. There's a big cost difference here, so there's going to be differences. But people tell us it's about 90% comparable, and certainly we have validation studies backing up the fact that if you train on this, it translates to the DaVinci. So this is a little bit out of date, unfortunately about a half year out of date, but this gives you an idea of some of the people that we place systems with. And this is just DV trainers. Obviously this map would be a hell of a lot more green if we had all the Skittle simulators in there. One thing you'll see is a big focus in Japan. That's because we talked about regulations allowing products in. The DaVinci SI has not been allowed into Japan. So we use a distributor in Japan, and they sell these things like crazy. I mean, it's like a couple every month. So there's an example of where restrictions has kind of actually turned into an advantage for us. We get money whether the skill simulator is sold or the DV trainer, but we get a lot more money if the DV trainer is sold. So that's sort of our preference. So how do you know if a simulator is any good and if it does what it's supposed to do? What you do is you do validation studies, and this is why you partner with universities and hospitals to test these systems and do research, decide whether the content you have is any good, what metrics you're measuring, which ones are most valuable. I personally believe that if you don't do validation studies, you may have nothing more than a glorified video game. So these are the types of validities that you might come across. Face validity, this is typically done with a survey. You have somebody sit on your simulator and they say, well, is it realistic? Does it behave like the robot? Or does your tissue behave like tissue? We've had everything with a star, by the way, is a study that has been done in most cases multiple times. Content validity, okay, it's realistic, but is your training content going to fit into a standard curriculum? Maybe I've got games you're playing on here that really don't translate to surgery at all. Yeah, it's realistic, but the training content isn't really preparing you for surgery. Construct validity is where it gets pretty interesting. If your simulator cannot distinguish the difference between an expert surgeon and a novice, all you got is a video game. Your expert better be able to sit down at your simulator and perform much, much better, even though they've never used the simulator before. That's because it's supposed to be like the real thing, right? So this is a very, very important study. Concurrent validity is how does the simulator stand up to the gold standard? The problem with DaVinci training is that we're not really sure what this gold standard is. Pig labs are probably the gold standard, but you can't use pigs in parts of Europe, England, for example. So people use all sorts of different types of dry labs. What we've done is, or I should say our research partners have done, is they've, in the beginning, we recreated Drylabs that were being used by various surgeons and put it in simulation so we could do a comparison. The weirdest phenomenon that's come about is now people are reproducing the simulation exercises and making them into the Drylab. So it's gone this like full circle, which it's kind of flattering really, but it's like, oh, you like those ideas, great. And then the real gold medal here is predictive validity. This is very difficult because this is how does this training transfer to the OR. Now in the OR you can measure things like, okay, how many times did your proctor have to take over during surgery? Or what were your case times? But really the long-term recovery of your patient is really what's important, but there's so many different factors that go into healing. They say a lot. I had somebody tell me once that hundreds of errors are made while somebody performs surgery, but your body is so adapted, it can overcome almost everything until sometimes these errors add up and you end up with either a bunch of small errors coming to be making things very complicated, or maybe you just have one big error. But it's very expensive, it takes a long, long time, but these are studies that are in the works, and this is really, really what you need to see for a simulator. So, what do you measure? These are some of the metrics that we measure when somebody performs, and this is an example of some of the reports you might get. For one, just at a glance, you can look at here and say, ooh, what are those red X's and warning signs? That can't be good. So right away you know if you see this report that you probably need to keep rehearsing. And these are some of the things that you would do. Time to completion, economy of motion is how efficient are you from moving to point A to point B. Are you colliding your instruments? When you collide your instruments, they can break, or even worse, slide off each other and run into tissue and damage that tissue. Are you dropping needles? Are you missing the targets when you're either applying energy or doing suturing? Are you moving your instruments when you can't see them? Experts will do this because they know where they are, but beginners shouldn't. They don't know where their instruments are, so when you get, you say, well, geez, where's my instrument? I don't know where it is. Meanwhile, it's, poking right into the aorta. So, where did all this blood come from? So, another thing about surgery, this is, I think, so many surgeons, chiropractors must really be really disappointed for surgeons that have gone from laparoscopic surgery to robotics. So instead of standing over a patient for hours at a time doing laparoscopic, you get to sit down in a nice little device like this. It's very ergonomic. But in the interest of being even more ergonomic, you have a clutch pedal. So you can really, it's sort of like a mouse, you can kind of pick up your mouse, move it over, and that cursor keeps going across the screen. That's what a clutch is. So very experienced surgeons will essentially only use wrist range of motion. Now this is, considering it can be a very, very long surgeries, in some people's first surgeries can be 7, 8 hours. So this is a long time to even be sitting here, but you can imagine standing over a patient, that's much, much worse. And then of course the more obvious ones are you applying energy somewhere that you're not supposed to be applying it, blood volume loss, and we do attach a score so people, those competitive surgeons out there can compete. But really, this is what you want to see. You want to see that after time, you're getting better with every metric. You want to see improvement. If you don't, one thing you can do is you can click on one of these metrics and you'll find out how you do on this metric for everything. So maybe somebody they're always have their foot on that energy pedal. They just don't care what they're touching. They're basically applying misapplied energy to everything. Maybe you haven't told them that's a bad thing. This happens quite often. People, you might ask a surgeon, well, why did you do that? And people say, well, no one ever told me I wasn't supposed to. Well, hopefully through simulation you can tell people some things that they should and should not do. So this is just sort of a list of some of the studies that have already been produced. You can see face content and construct have been done multiple times. We have a few on concurrent. This is also out of date. This is some of the pending research. I know Columbia has published since, same with Johns Hopkins, UC Irvine. And then there's the studies keep rolling in, and frankly, the more we can do, the better. And the reason it's important to keep doing it is our content keeps changing. We keep adding content and there's more to do. So this idea of validation never stops. And ours is there's maybe one other company out there doing DaVinci simulation now, but we're the only ones that have extensive validity, and more importantly, we didn't validate it ourselves. So it always cracks me up when somebody does a validation study on their own stuff and then say, look, it's validated. It's like, geez, yeah, you're not biased or anything. Again, why you need independent research partners. So we are going to go to more advanced applications. Here we are back. This open frame idea is actually embedded. That is actually our first prototype. One of the things we found is that aesthetically that configuration wasn't very pleasing. So this is why we have this nice shell on it, an adjustable height stereoscope, things of that line. It's amazing what a little aesthetics and packaging will do for a product, which was essentially almost as functional as the other design, but just didn't look like the robot and kind of wasn't as cool. This is just some of our earlier work in processectomy. The one I told you about was too complex, and frankly, the simulator's not very good either. So we've moved on and got much better. Eventually, we'll go for a full circle and get back to doing procedure-based simulation like you're seeing here. There's also there's only one program right now called the Fundamentals of Laparoscopic Surgery that's under the American College of Surgeons, where you actually do hand-eye motor coordination testing to become a surgeon. This is relatively new. The idea is, though, that laparoscopic surgery, believe it or not, some people will make the bold claim that laparoscopic surgery is going to die out, and you're going to have only robotics at some point. So we're working with all the medical boards, the three different robotic societies, CRSA, SRS, and MIRA, all to develop this program. And then the idea is you have one base package of fundamental skills that everyone needs to learn. And then you have advanced packages that might be urology dependent, gynecology dependent, and so forth. And then let's not forget about the other players that are involved. Team training. You always have a patient side assist, or typically, and they're handing you in sutures. They might do some retraction. They might provide suction. This is getting a very competent patient side assist. It is difficult. So why not bring this in where you can have essentially a laparoscopic system on one side and you're communicating with the consult side surgeon and really getting that teamwork down. Now, we definitely want to get to more procedure specific. And there's a lot of companies because this is what everyone wants, right? I remember sitting down and somebody tried our early exercise and you're like, all right, take me to the prostate. And I was like, well, hold up here. We're doing very basic stuff. Now, there are certainly people out there because this is what people want. People will try to deliver it. But then if you really press people, you say, well, how accurate are these procedure-specific simulators? Like, well, I don't know, maybe 10% of it is accurate. But it's really good at teaching you the steps. Well, so is a $10 multimedia disc. Instead of a $100,000 simulator. So you got to be very careful when you want to go into very procedure-specific type procedures because you need to not only suspend disbelief, but if you model incorrectly, imagine you retract a tissue in a simulator and everything's fine. Next thing you know, you get on there and the tissue deforms completely different and you rip that tissue. You don't want to teach people inappropriately because you're just basically a glorified video game, regardless of whether you're learning the steps. So we're taking a pretty slow approach to making sure that when we do this, it's going to be accurate. And then when it comes to full procedures, I look at it more like scenario training. If you're doing flight simulation, you don't always fly from the same city to the next city at the same weather conditions. When you do flight simulation, their goal is to make you crash. They're going to add weather, you're going to have to go to different places. Everything they do, they're trying to get you into that tailspin so they can see if you can get out of it. That's what needs to happen in surgery simulation. You need different scenarios. You need to be exposed to the types of complications that you might not find in a normal caseload. So that's truly going to be an incredible value of simulation in the future. And then the holy grail really is to import patient-specific data and warm up and practice on a virtual patient that you're going to be operating on maybe that same day or the next day, and using some of the information from your planning in that surgery. So just real quickly, I'm going to show that we have not only done robots for surgery. We did dabble a little bit in other types of robots. And here what you're seeing is these are two PackBots. This is made by iRobot, who makes those vacuum cleaners. And we talked to our partners at iRobot and Dartmouth, and they said, well, you know, we're having a real hard time making this robot open a door. I'm like, oh, geez. So all the terrorists got to do is put a bomb in a room and you're safe. And the reason is they have a very awkward control. It's like a joystick. So here you are, you're kind of huddled behind your Humvee. The bad guys are looking for you, and you've got this robot out there, and the robot's going up, over, turn. You know, just really, really slow instead of this dexterous manipulation that you find in the intuitive robot. So we took, you know, they said, well, can you make one robot work? We went a step further. We took two virtual robots, attached it to our two-handed system, and created just this concept video. And we did this one demo. It was a bunch of children, kind of the ages of 10, and they were stacking these complex blocks and stuff using the robot, using our interface, where expert robot users couldn't do this. It just shows you just the application of a different interface can really change the way existing technology is used. So here we go. We model it up in VR. Now we apply it the real thing. In this case, they're using two of our one-handed systems, but here you see the real robot. And that was Jake from Dartmouth. And the application here is a mine shaft cable is broken, and you're trying to reconnect this cable in a toxic environment. So this was a concept of how two robots might be controlled and used together with two hands. And I've always felt that this is the way development should be done. You know, we talked about the modeling before you build the real thing. Well, why not mock up a virtual robot, try your procedures, make adjustments, whether it's arm lengths or whatever it is, to make sure that your concept works before you build the real thing. You might have saw that the DaVinci robot has the patient straddling the robot. You know, so it's really awkward. You know, the reason is because they thought it was going to be used for mostly cardiology. They didn't really plan for some of these other types of applications that it eventually ended up being used for. So maybe if they had planned for it and tried it in VR, their designs would have been different, and they would have ended up with maybe a simpler type of design. And we are looking at other applications for surgery. Not so much, we're trying to stay focused in robotics, but we definitely did our thing with open surgery. Matter of fact, this initial frame was kept open for the reason that it could double as open surgery. You have this 3D display back here. It's projecting to where the user's hands are so that they feel what they see. It's kind of a novel platform there, but it turned out every time I'd go out and try to show this, especially in military people, they go, where's that robotic simulator I keep hearing about? So everybody kind of wanted the new technology, so we kind of went with what we thought we'd get a little bit more bang for our buck. But in this application, you're feeling these pieces of shrapnel come out of the hand, and you're seeing stress-strain analysis to give you an idea of tissue strain that you might not see in real life. So anyways, that's just some examples of the technology that we've been utilizing, and I'll just sort of open it up for questions now.
Thank you, Dr. Berkeley. That was great. Oh, hands up already.
Thank you for the talk. This is a really exciting technology. And I just have two quick questions. And the first one is, how large is the market according to your estimation? And the second one is, can this technology be used for telesurgery?
Good. Okay, so first, if I understood correctly, what's the size of the market? And then what's the size, or can it be used for telesurgery? Well, this is interesting. I'll answer the second part first. Computer Motion, the company we were first supposed to use work with, they did do telesurgery. You might have saw the news application. And I'm sorry, I thought that I didn't get to get the title changed in my talk in time, because in reality, the DaVinci is not a telepresence robot unless you consider the next room telepresence. But Computer Motion had this technology. It was being utilized. Intuitive bought that company, shelved it. So this is doable technology, but it's been suppressed by the monopoly that is Intuitive Surgical. So it may be a while, even though it's possible, before telesurgery comes back. As far as the size of the market, it's a real good question. Let's see, you basically, we kind of look at it for us that Intuitive sells on the order of 100 robots a quarter. There's about 200 robots out there. We feel we can sell at least one simulator for every robot that's out there. So it's at about 2,000. It grows by about 100 a year. But here's the thing about what we're doing. This is an Xbox. This isn't the end all. You think about how many surgeries and applications there are out there. Once you have your hardware base in place, now you can go back and sell software over and over and over again. So the size of the market, when you consider the reoccurring business that you have, you saw that nice curve that Mark did, where eventually you saturate the market. You got to have that follow-on product, and for us, it's going to be software applications. Any more questions?
One more question? Yep, the professor. We're going to put it, no, you can talk, I'm just going to.
What sort of IP protection? What's the nature of your IP protection?
We started patenting our stuff very, very early. And I think we have 2 patents approved now. The first one we went after was our one-handed system. And it is amazing. It took us 7 years to get that patent.